This video is going to help us make a distinction between the terms mass and weight, which are often confused because they seem to mean very similar things. But we're going to find out there's some definite, distinct differences that we need to be aware of. To define them, mass is just simply the amount of matter in an object. This is a constant value. It doesn't increase, it doesn't decrease on a relatively, in the short term, I guess. People can start off small, and as they get older, they get bigger, they acquire more mass. But for the most part, from a day to day or week to week kind of a basis, mass is a relatively constant thing. Weight is not. Now, I'm not talking about losing or gaining weight, I'm simply talking about the force that causes weight. In this case, it's the gravitational force. Weight is the amount of gravitational force that acts on an object that causes us to have weight. Now, we have to kind of look at this term force, and we haven't gone through a lot of this till now. So the first thing we would like to do is just simply define that term. So what I'm going to do is get a pen tool and define this force as a push or pull. Very simple terms. If I'm pushing on something or pulling on something, trying to make this move. It doesn't have to make it move, but it's attempting to make that move. That is a force. Now, I want to next look at just a very simple demonstration, or a very simple idea of having a box sitting on a relatively flat surface, nor any curving in the lines. It's strictly unintentional. And this thing is being pushed by a force, F. And what we want to do now is look at all the other forces that are not as obvious that might be there. For example, there's going to be a force that's pushing against this that we would call friction. There's another force that pushes up on this box. That was what we would call the normal force. Now, I guess before we get too far ahead of ourselves, friction is a force that opposes motion. It stops things from moving. We know if we push on this box, eventually, intuitively, we know it's going to eventually come to a stop. Friction is the reason for that. It works against our motion. We know that there's a normal force going up because there's one other force that we haven't drawn on here going down, and that's basically equal to the weight of the object. And we found out from our earlier video about balanced versus unbalanced forces that if it's anytime you have a force, if there's not something balancing that force, there's going to be motion caused. So when we have weight pulling something down, the normal force pushes up against that, and that basically causes that to stay in equilibrium in terms of the y-axis. A better way of drawing this diagram would probably be using a free body diagram where everything is drawn from a central point. So I'm just going to really quickly sketch that. And you can see if all these forces are equal, it doesn't mean that the thing's not moving. What actually happens is this thing will continue the motion that it has. Now, if it stopped, obviously there's not going to be any motion. But if this, sorry, that's an F, not a T. If this force pushing it forward is equal to the frictional force pushing it backwards, then it will continue to move at the rate that it's moving at. If the friction is more than this force, this pushing force, then what happens is this object will slow down until it stops. And then the friction stops because there's no longer any movement. You have to have movement in order for friction to happen. So this is what we would call a free body diagram, which makes it a little bit easier for us to do that. So the other thing that this points out is weight is a vector, where mass is not. So this will change if I go to another planet or some other place or somewhere possibly out in space where there's no gravity. So let's try to kind of wrap this up here, or at least kind of summarize. If I want to talk about just simply mass, I'm going to put point number one, it's constant. It is measured in kilograms. It is a scalar quantity, meaning it has no direction to it. Weight is based on location. Measured in something called newtons, which we are familiar with. It's a vector quantity. Which says it has direction. And can be added to other vectors, as we showed you in this diagram here. Here you can add and subtract the normal force versus the weight. If these two things cancel each other out and equal 0, we know this isn't going to move. If the weight is more than a normal force, well, then this would have to move downward. So the last thing is there's a formula based on Newton's second law. Weight equals mass times gravity that we're going to use. If I have planet X, we'll just call this, where gravity is equal to 12 meters per second squared. That would be something like a little bit bigger than the Earth, obviously. When I go W equals mg, you know, if I have a little stick person here, they're being pulled down by, that's a down arrow, sorry. They're being pulled down by the weight that's given to them by that planet. And let's just say this person has a mass equal to 70 kilograms. To find this, I'm going to go 70 kilograms times 12 meters per second squared, and it's going to give me a total of 840 newtons. If I go to planet Y, we'll say it's a little bit smaller than Earth. If I take that same person here, who has a mass that's equal to 70 kilograms, and put them on this planet where gravity is equal to 5 meters per second squared, let's say. If I just do a simple W equals mg, 70 kilograms times 5 meters per second squared, it's going to give me 350 newtons. So you can see that's what when we say weight changes, we're talking about how much gravity is pulling on you. On a larger planet, if you could travel there somehow, you can see you'd have a mass of 840 newtons. On a smaller planet, you can see you'd have a weight, misspoke there, bad misspeak there. Let me start over. Go to this planet X, greater gravitational field than the Earth, you have 840 newtons of weight. Here you have 350 newtons of weight, but the mass on both planets was 70 kilograms, which was the same. So that's our mass versus weight discussion, and make sure you kind of keep those things separated in your mind. An important part here is weight is a vector. Weight is a vector quantity, so it can be added to other vectors, where mass is just simply a scalar.